All right, welcome everyone. I'm Norman Wildberger, and we're carrying on with this discussion of covering spaces. Today we're going to look at some examples of some of the results we talked about last time, and I'll introduce this idea of a universal covering space and how to construct it. All right, so we're looking at the situation where we have a covering space, P from X to B. And we saw last time that if we look at the induced homomorphism, P star from pi of x to pi of b, say b, where x is a point in X mapping to point B in B, then this is injective. And that tells us that we can sort of identify this image, P star, or actually we can sort of identify the fundamental group of the covering space with a subgroup of the fundamental group of the base. All right, so I want to illustrate that with a few examples to make it a bit clearer. So I guess the simplest example is when we have our familiar circle as the base, and we choose some finite cover of it. Let's say a 3-sheeted cover. So this is a cover where the inverse image of any point here has 1, 2, 3 different inverse images. So sometimes we might say this is a 3-fold cover or a 3-sheeted cover. All right, so both these spaces are actually topologically circles. B is obviously a circle, but X is also a circle topologically. So both of them have fundamental groups which are very familiar. The fundamental groups of both of them are just essentially the integers. They're just cyclic groups generated by one loop. So let's call this the base B. Let's choose one of these inverse images to be our base here. Let's say this one here and call it X. So what do the various generators look like? Well, of course, we might say this loop here, maybe we'll call that alpha, so that the fundamental group of B, based on B, is generated by alpha. In other words, it consists of all powers alpha to the n, where n is an arbitrary integer. And upstairs, we have also a single generator starting here, and let's go around the same direction. So in this direction here, go all the way around, This is a loop, okay? And we'll call that loop, say, gamma. So the fundamental group of X, with respect to X, is also generated by gamma, in the same way that this fundamental group is generated by alpha. All right, now let's look at this induced homomorphism. The map P induces a map from loops up here to loops down here. And what is the image of this fundamental loop gamma up here? What's the image under this induced homomorphism? So the image P star of gamma is, so how do we calculate that? Well, we look at what happens to gamma when we project down. Okay? So let's start with this point here. Its projection down is there. So as we move along gamma like this, the inverse image, or the image under P is moving as I'm showing you here. So at this point we've gone around once, but gamma keeps on going. Now we've gone around twice, and finally when we get back to the origin, we've gone around 3 times. So the image of gamma under the induced homomorphism is alpha cubed. And of course, then that extends to powers of gamma as well. So for extend that, we could say that if we take some power like gamma squared, if we go twice around gamma, well, the image will be going twice around alpha cubed. In other words, it will be alpha to the 6. And so we see that p star of pi of x is just the subgroup of pi of b generated by alpha cubed. It's the subgroup generated by alpha cubed inside this infinite cyclic group. Now we're thinking multiplicatively, but when we're working with the integers as a group, we can also think additively. And if we think additively, well, then what we have is a situation that's quite familiar. We can think of the original downstairs group as essentially being Z, isomorphic to pi of b, and then this image under this map is going to consist of all multiples of 3. So it's going to be the subgroup. This is p star of pi of x inside pi of b. So it's basically multiples of 3. Or in additive notation, 3z inside of z. Let's look at another example. So example 2. Suppose we consider the covering P from a torus to the torus, given like this. So here's our base space B, which is a torus. And then up here, we're going to make a bigger torus, 0, 1, 2, 3, 0, 1, 2. So this is X, which is also a torus, with this side identified with this one, and this one identified with this one. And our map is going to be the same one we considered last time. It's going to be the map that sends the point xy to just xy mod 1. So this is kind of a planar version where we don't have some picture in space, but we also could try to make a picture in space involving 2 tori. And the map is one that sort of wraps 3 times in this direction and twice in the other direction. All right, so let's look at the fundamental groups. What do we know about the fundamental group of a torus? So the fundamental group of T is, well, it's isomorphic to Z plus Z. And say down here, we can see what the generators are in terms of loops. So there's one loop corresponds to that path there, alpha, which we might draw like this. There's alpha. And then there's another one, beta, in this direction, which we can draw as that loop around that little circle there. Okay, and upstairs, well, it's still the same space, so it has also 2 generators. Well, let's call this one gamma, and this one delta. And The relations in the fundamental group are basically that alpha and beta commute. So that the relation is alpha inverse, beta inverse equals the identity, or equivalently, alpha beta equals beta alpha. Similarly up here. And so what is this homomorphism of fundamental groups that's associated with this picture? Well, so P star will send gamma to. So what happens if we go along this way here, from here to here, and look at the image mod 1? Well, as we go along here, the image is going like this. So at this point here, we've already gone along alpha. We're basically back to where we started, because this point is the same as that point. Okay, and so now we keep on going here. We traverse this alpha again, and we're back to where we started. And we keep on going, we traverse it again, we get back to where we started. So we see that gamma gets sent to alpha cubed. Essentially the same story as we had in that previous example. But also delta, what's happening to that? Well, it's the same kind of story. As we go from here to here, the image goes up like this, and then we're back to where we started, and then we keep going, and then we're back to where we started. So we've gone along beta twice. So the image is the subgroup generated by alpha cubed and beta squared. So this is all words in alpha and beta, commuting words in alpha and beta. So things of the form alpha to the n, beta to the m. Then this subgroup is going to be things of the form alpha to the 3k, beta to the 2l. That's going to be a subgroup of index 6, actually, of this group here. And let's have a look at one more example. Let's consider the situation where we have X being this space, just a one-dimensional graph covering our wedge of circles B. So I remind you how this covering map goes. These 2 points here get both mapped to this point down here. Let's call this point A. Let's call this X, and this one X prime. So both X and X prime get mapped to A. And the alpha loops get covering this alpha here. So we can just take this thing, imagining it made out of string or something like that, and we take these 2 points here, and then we map them both onto here. And then this loop alpha here gets sent to, covers this one, as does this one here. This one also gets sent to here. So we end up with these 2 loops alpha over this one, and then this beta gets mapped to this one, and this beta also gets mapped to this one. So we have 2 loops going over here and 2 loops over this one. That's the covering. Okay, at the level of fundamental groups, what happens? Well, here the fundamental group, pi of B, say based on A, just consists of words in alphas and betas, but not commuting now. So just words in alpha and beta, some kind of free product of alpha and beta. So things of the form alpha cubed, beta squared, alpha to the minus 5, beta to the 7th, alpha 1, for example. That'll be a typical element in this thing here. How about this space here, pi of x? say we have to choose a base point. Let's choose this x as the base point. What are the various loops that we can consider there, and what's the fundamental group look like? Well, there are various loops that we can consider starting at x. We could go like this, or we could go like this, or like this, or we could go like this, or maybe like this. There's quite a lot of possibilities, lots of loops to choose from at x. Let's choose the following ones. Let's choose, okay, I'm going to write them like this, hopefully without confusion. Alpha squared. Okay, alpha squared means this loop. You go down that alpha and then up that alpha. That's a loop. And beta squared, that's the loop that goes along this beta and then along this beta. It's another loop. And maybe alpha beta, which is alpha followed by beta. So it's this loop here. So those are generators of the fundamental group. Other loops can be written in terms of those products. So for example, well, you know, because the product of this loop with this loop is this loop here. So these three form a generating set, generate. And this way of writing the loops makes it completely clear what the images are going to be. Okay, so under P star, well, alpha, this what I'm calling alpha squared there, just goes to alpha squared down here. So as I go around here, alpha, alpha, the image goes alpha, alpha. So these to be thought of is inside pi of b. So in other words, we're considering the subgroup of all words. Here we have all words in alphas and betas, and here we're considering the subgroup of words, which are words in alpha squared, beta squared, and alpha beta. Things like alpha squared cubed, say beta squared to the minus 1, alpha beta to the 5th, alpha squared cubed. Okay. That's a word in pi of b, which is a special word. It's in the image of this group. All right, so we've got this nice idea of associating to a covering space a subgroup of the fundamental group downstairs. And this gives us the idea that we should make covering spaces correspond to covering spaces of B correspond to subgroups, or maybe conjugacy classes of subgroups to be technical, but let me just say subgroups of pi of b. And to make this sort of more clear, what we're going to do is we're going to identify the covering space which is associated to the smallest subgroup. So the smallest subgroup of pi of b is just the identity. And it's going to correspond to the biggest covering space. of B, namely the universal cover. The universal cover of B. And so we want to understand how to get the universal cover of B from B. Well, let's look at an example first. If B is equal to the circle, S1, the universal cover is one that has fundamental group, just the identity. It means it's simply connected. That's going to be the infinite cover consisting of the line. That's the universal cover. Of all the coverings of the circle, this is the one that's distinguished by the fact that it doesn't have any non-trivial loops in it. It's simply connected. How would we get this universal covering if we only lived in this space B? Suppose we lived in this space B and we were trying to imagine the universal cover. We didn't, say, have 3 dimensions to think about. Well, the idea is the following. Suppose we pick a base point, say A, and we're going to sort of think of a base point here. Let's call it X. How could we get this X from A? So how could we get this X from this base space B? Well, what we do is we're going to look at curves, paths in B, which start at A. Homotopy classes of paths which start at A. So we're going to choose any path. Let's choose this one here. Okay. So that's a path alpha. Alpha is a path in B starting at our fixed base point A, but not necessarily ending at A. And it can wrap around as many times as we like. What we're going to do is we're going to note that in this case here, we can lift this map. In this case, this is a covering. We can lift the path alpha to a path up here, and we get the path that looks like this. Starting here, we're going in this direction, so we're going around, got around once, and then a little bit more. So maybe we're at that point there. Okay. So if we lift alpha to X, we get a path from X to, well, to some point. To a point in the this universal cover. Maybe we'll give the universal cover a special name, put a tilde on top of it. What's the point? This is the point right here. Say Z. Now if we change the homotopy class of this path alpha, if we wiggle this path alpha around a little bit, if we change it by making it something homotopic, looping around a little bit, well, the effect is not going to do anything much to this thing here. It's going to be a corresponding little homotopy up here, but we're going to end up with the same point Z. So Z is independent of the representative of the class of alpha. It only depends on the homotopy class of alpha. That means we can think about Z as being the homotopy class of alpha. This is a kind of simple-minded idea. Sorry?
Have you line alpha back to A?
Not if its endpoint is fixed. So we're gonna go along alpha to wherever it stops, and we're gonna stop alpha at that point there.
With your homotopic classes, you already have that point there. So it's not like homotopic classes in the way that you're talking about.
They're homotopic classes in the sense of having a fixed a starting point and fixed initial point. When we've done homotopy, we've always fixed the first point and the last point in our homotopy.
Oh, right. They will always make.
Yeah, because sort of, if you remember that square, we always sort of insisted that the first.
Before it was always starting and ending at A.
It was starting and ending at A, but more generally starting and ending at B, say. So we can move it along, but we have to stay at A and stay at B fixed to the endpoints. All right, so the idea is to identify the point Z with the homotopy class of this path alpha. Identify Z with the homotopy class of this path alpha. And that's how we construct the universal cover in general. So this is how we define, say, X tilde, the universal cover of a space B. We fix a base point A in B, and then define the points of this universal cover to be homotopy classes of paths in B starting at A. So i.e., we think of things like this, where alpha is a path in B starting at A. All right, that's what it is, sort of as an object. And we also need to define this map from the covering space down to the base point, the covering map. To do that, this is defined by so we have such a homotopy class of paths starting at A. We define its image under P to be, what should we define it? We want to associate to this point Z a point down in the base space, a point below it. But you can see from the diagram here that the point below it that we want to consider is going to be the endpoint of the path alpha that we started with. The other endpoint. The beginning point is A, but it has some other endpoint in B, and that endpoint is what we're going to do. That's what we're going to project this point in the cover to. So this is going to be the other endpoint of this loop alpha. Not loop, this path alpha. It's a point in B. All right, so let's look at some examples. So Let's look at the torus. Let's choose a base point. And let's ask ourselves, suppose we didn't know what the universal cover was. What would happen if we just look at paths in the torus? Arbitrary paths starting at A. What are all the possibilities? Okay, so we're allowed to choose an arbitrary path, can go around, and it ends up at some point. We're allowed to homotopy that path, keeping the endpoints fixed. We're allowed to sort of stretch or tighten the string. But we're basically interested in that particular path. What kind of thing does it actually define for us? Well, it's not so easy to see in this picture, but it's a lot clearer to see if we look in the picture of the plane. So let's look at the picture with our torus sitting inside the plane in the usual square 0, 1, 0, 1. There's our torus with sides like this. And we might as well choose our base point to be this corner A here. All right, so the path that we drew on the torus maybe did something like this. I probably didn't, not exactly, but let's say something like this. It went like this perhaps, and then at this point it has to cross here, and then maybe it went up here, and then maybe it went down here. Let's just say it did that, all right? So that's sort of stage 1, 1, and then 2, 2, and it ends up at this point 3. Okay, that's a path in the torus starting at A. Now, how can we visualize what that path actually is? Well, what we can do is we can just work in the plane and extend the plane with this mod 1 condition that we've seen before, and just free ourselves from wrapping around and keep on going. All right, so I'm going to look at another path now. So I'm going to follow this path along here, but instead of going back over here on the torus, I'm just going to keep on going. In the plane. So this was 1, and then this was 2. And then I'm up at this point here, which is the same as down here. On the torus, I had to go down, but I'm not going to go down. I'm just going to stay where I am, and I'm going to keep going up like this. So naturally associated to this path on the torus is this path in the plane. And this path in the plane has a well-defined endpoint, and that endpoint is the point that I'm going to think of as representing this homotopy class. If I change the homotopy class of this path, I'm just changing it a little bit, but I'm not actually changing its endpoint. So in other words, this point is a point in the universal cover. In other words, the universal cover is just the plane itself. So the universal cover is just the plane. The whole plane. And what is the projection onto the torus? Here's the torus, that initial square there. Well, the projection is just the familiar one, that sends a point x, y to x, y mod 1. That would send that point to that point there. And the plane is indeed simply connected. It does not have any non-trivial loops in it. How about the projective plane? P, projective plane. Well, we have only seen one cover of that, and that's the sphere. This is a two-sheeted cover. Since the sphere is already simply connected, this is the universal cover. And what about a two-hole torus or a three-hole torus? So what happens if the base space is a two-hole torus? What is the universal cover of that? Well, that's not so easy to lay out in complete detail, but I'll tell you what the rough idea is. The rough idea is to think of the two-hole torus in terms of its planar representation, in terms of an octagon with sides A, B, A inverse, B inverse, C, D, C inverse, D inverse. And then what we want to do is we want to do something like we did with the torus over there, is to put copies of this thing around it so that when we move along here, come out some other side, probably around here, then we can interpret that as movement in some larger domain outside it. Okay. And it turns out that what we need for that is hyperbolic geometry. So what we need is the hyperbolic plane. And we can embed this octagon in it in a suitable way with an octagon regular embedded so that with each turn angle, so this angle is actually a 1/8. Which means that there are, in fact, 8 congruent octagons fitting around such a vertex. Now, you can't do that in the ordinary Euclidean plane, but with the magic of hyperbolic geometry, you can do that in the hyperbolic plane. And so once you have this octagon with the right size so that you can fit 8 isomorphic copies of it around each vertex, then you're in a position to play the same game as we did over here. Then you can extend any path in the base space to a path in the larger hyperbolic plane. And then it turns out that the hyperbolic plane, or this disk, is then the universal cover of the two-hole torus. Okay, that's a story that takes quite a lot of explaining to do it correctly, so I'm not going to do it. I just want to give you a rough idea. Okay, so that the final picture that we have is we have the space over here and the universal cover. The sphere itself is already its own universal cover. The projective plane has cover S2. The torus and the Klein bottle both have universal cover of the plane. And then all the other surfaces, all surfaces with negative Euler characteristic, have universal cover the hyperbolic plane. So we get this kind of division. This is sort of the Euclidean. This is chi equals 0. and chi positive is spherical. So the positive Euler characteristics, the sphere and the projective plane, have covers which are the sphere. The two surfaces with Euler characteristic 0, the torus and the Klein bottle, have Euler characteristic, have universal cover, the ordinary Euclidean plane, and all the other surfaces, 2-hole torus, 3-hole torus, and various cross caps that you can put on that, have universal cover the hyperbolic plane. Okay, so let's have now a look at how the fundamental group of the base connects with this universal cover. And I'm going to draw diagrams with this one because it's simplest. All right, so here's our base space B. Here's our universal cover, X. And we'll choose a base point A here, and we'll choose a base point X here. So an interesting aspect of things here is that the fundamental group pi of B, based at A, acts on the universal cover. And to describe this, let's have a look at, first of all, how it acts on the fiber. So first acts on pi inverse of A, which is sometimes called the fiber above the point A. So pi inverse, P inverse of A. So there's the projection P. If we look at the inverse image of A, it's got not just this point X, but also all these other points, maybe X1 and X2 and X3 and so on. These points are called the fiber above the point A. So how does this group of loops here act here? Well, if alpha is an element in the fundamental group of B based on A, then we associate to it a permutation of P inverse of A. How? So let's choose our loop to be, let's say, the one that goes around twice. Okay, there's an element in the fundamental group of the base. So what we're going to do is we're going to take any point in the fiber, let's say X, and we're going to lift the path alpha to a path starting at X. So to X in P inverse of A, we lift alpha to a path starting at X. Namely, as we go around once, twice, we go around once, twice. There's the lift of the path alpha to the universal cover. It's no longer a loop. It was a loop down here, but it's no longer a loop here. Here, rather, it's taken us from the point X to the point, in this case, X2. So the image, or the endpoint of this path, is another point in the fiber. So in this way, the fundamental group acts on the fiber. It turns out that this action extends to an action on the whole universal cover. This action extends to an action on all x tilde. In other words, to every loop here, for example, say if we just look at a generating loop, we get the sort of skew motion of the universal cover, which is what you get when you go up exactly one floor above the point that you're starting at. So for example, if we look at some adjacent point y, we can also lift it to a new point y2. So the whole space gets moved up by the action of this loop down here in the base space. All right, so it's in this way that we can end up seeing how other covers of the base space B can be generated from covers from the universal cover. So using this, other covers of B can be created from subgroups of pi of B. All right, so this is a kind of a rich story. I'd like to give you a reference. So Alan Hatcher's book on algebraic topology, which is a lovely book, and it has the big advantage that it's available online. Has a very nice section on covering spaces and these sort of so-called deck transformations that goes into a lot more detail and about covering spaces and their interaction with fundamental groups. So in our next lecture, we're going to look at a different aspect of algebraic objects associated to spaces. We're going to look at the homology of a topological space. So I'll see you then.